Hello again. This is our controls class. We are continuing. Now we have seen that there can be systems with one input and one output. And this system can have a transfer function so that y of s is equal to g of s times u of s. We have seen this. Let's start with g of s is equal to n of s by d of s. These are polynomials. You know that if d of s has roots lambda 1, lambda 2, lambda 3, etc., then Laplace inverse of g of s will be of the form I should not say I, a k e to the power lambda k t sum on k, maybe with this part is with repeated roots. You should be familiar. I will not spend time discussing this part much. If the roots are not repeated, that's all there is. These are coefficients. You can find it by a partial fraction expansion, and you've done homework on this. So you're familiar with this idea. Very good. What happens for a step response? Step response means u t is this, comes with 0, jumps to 1, and goes like this. Okay, so the Laplace transform of this is 1 by s. Let's go to Maple, which is a software package that does calculations of an analytical nature. So the Laplace transform of 1, well, that didn't work. The Laplace transform of 1 is 1 by s. Okay, that's what I'm using here. So then what happens is y of s is equal to g of s times 1 by s if g is stable. Okay, stable, that means all roots in left half plane. Then y of s times s, this one as s goes to 0 gives you little y of infinity. This is the final value theorem. You are familiar with that. When you multiply by s, basically you cancel this, and so you look at the s equals 0 value of that, and that is the final value. Similarly, if you have the same expression but you look at s going to infinity, then you get the initial value. And this step response is built into MATLAB, which understands transfer functions. So MATLAB is another software package which Maple is not essential, MATLAB is essential for you. So let me say n equals 1, 2, d equals 1.36. These are actually the coefficients of polynomials. They are to be understood like that. So this polynomial is s squared plus 0.3s plus 6. Okay, I can, in MATLAB there is a built-in command to find roots of polynomials, and you see, if you think of it as a spring mass damper, the mass is 1, the spring is 6, so the frequency will be about square root of 6. There is a relatively small amount of damping, so there is a small negative real part, and that is what we get over here, you see. So this is not some mysterious thing. These are very useful commands. I can remove these gaps in the response in MATLAB by a useful command called format compact. You may like to use that. I will say G is equal to TF, that's transfer function n comma D. It understands S, so now it understands that this is a transfer function. This transfer function is called strictly proper because the numerator order is less than the denominator order. If the numerator order would be equal to the denominator order, we would say proper, and if it is higher than the denominator order, we'll say improper. Okay, so now we come here and we say step response of G, and as we discussed, S going to 0, 1/3, so we expect it to settle at 1/3, and S going to infinity, this is S, this is S squared, so 0, so we expect the the step response to start from 0. Okay, there it is. I can zoom it. You can see that it is going to 1/3. Here you can see that it is going to 1/3, and here you can see that it starts from 0. You see it starts right from 0. Okay, so that is what the step response is. Now let us look at something like this. Let us say n is the same but d is negative. This one is going to be unstable, right? So if I look at roots of d, you see it's got positive real parts. If I say g is equal to that, that's got positive real parts. If I look at the step response, you see it is growing exponentially. This is growing quite fast over here. You will see that it's growing exponentially. It's oscillating and growing. If we zoom into a narrower area, then you will see the oscillations and the exponential growth more clearly. Very good. Now we are going to think about feedback. So let us work with that G for the moment, and we will say here is U. This is G. Simplest possible case is to just feed this back here. So as we have worked out before, the closed loop transfer function, which I am just calling H, is equal to the forward path, that is G, divided by 1 plus the product of the forward and the feedback path, which is G over 1 plus G. Now G is equal to S plus 2 over 1 minus 0.3 S plus, sorry, not 1, S square, and then plus 6, and more generally n by d, then G over 1 plus G is equal to n by d over 1 plus n by d, which is equal to n over d plus n, and then that becomes S plus 2 over S square minus 0.3 S plus 6 plus S plus 2, which is equal to S plus 2 over S squared plus 1.7 s plus 8, and you can see that the simple act of this, which we call unit feedback, unit gain, just no gain, gain is 1, right? This has made it stable, and we will see here in MATLAB if we say h is equal to g by 1 plus g, MATLAB does elementary arithmetic with Laplace transforms, but it does not cancel properly. You see over here the denominator is factored above and below, it could be cancelled. It does not cancel it. This occasionally leads to some numerical errors we want, but in this case I think it will not. Okay, so what we will do is we will look at the step response of h, and it's going to be 1/4 over here, just like here we expect it to be 1/4, 2 by 8, and from here we expect it to start at 0. See the discussion earlier. So over here also we expect it to start from 0 and settle at 1/4. There it is, starts from 0 and settles at 1/4, and feedback has made the system stable. Very good. Sometimes direct feedback may not make the system stable, and we will look at that again. So now let us look at this system once again. Now the denominator is has got only left half plane roots, but over here let me put minus. So what happens now, g is like this. The poles or the roots of the denominator polynomial are all in the left half plane, but the zeros, which is the roots of the numerator polynomial, include at least one that is in the right half plane. In this case there is only one, and it's in the right half plane. Let's look at the step response of this g. This one is stable, there is no problem. You see, it's stable, but what is interesting is that the steady state value is minus 1/3, and when we look here something interesting happens. Pay attention to this. Something interesting happens. The initial response is in the opposite direction to the final response, and you can imagine that this can sometimes lead to trouble. Suppose you use feedback and suppose you use a gain. This is one reason why a large gain may cause trouble, because you want it to go right, you push hard to the right, it goes left, and you say no, that's not what I want, and you push even harder to the right. You see something like this, but of course mathematically we should try to understand that, and that is what we are trying to do here. So we'll come here and we will see what happens now. So now our n is equal to s minus 2, and let us say that in our forward path here we put a gain k, and so our closed loop transfer function is k s minus 2 over s squared plus 0.3 plus 0.3s plus 6 plus k s minus 2k. Okay, very good. And what do we have now? Now we have this 0.3s is not a problem. This is positive, this is positive, but we will get instability for k bigger than 3. Okay, let's come here and look. It's no problem. We'll say h is equal to 2.7 times g by 1 plus 2.7 times g. Once again it will not do the cancellations, but don't worry. Let's look at the step response of h. We expect it to be stable. There it is, stable. It goes to the goes up and then settles down at some other funny value. That's a different matter, but it is stable. Okay. However, if we say h is equal to, let us say 3.3, Now you see it was going along like this and it has become unstable. It sort of really zoomed away over here. Okay, so if I zoom into this part of the picture, you will see that it came and exponentially zoomed away. This is because it is unstable. All right. This little exploration brings us to something that's really important in classical simple control theory, which is called the root locus plot. Okay, so what's the root locus plot? So let us say G is equal to N by D. That's fine. We have once again the same, we keep drawing this, right? We'll have a K here, we'll have a G here, we'll have a Y. We could not have this here and have the K here. If we had this, the green one would be Kg by 1 plus Kg. The blue one will be G by 1 plus Kg. You can see that this response is just K times that response. Stability for the two is the same. Okay, very good. And so for stability purposes, we might as well put the K here. It doesn't matter. Let's not have this. So then what happens? How do the poles behave? How do the closed loop poles behave as K changes from 0 to infinity? Okay, these poles trace paths in the complex plane, so the paths of these poles is plotted on a graph that is called the root locus plot. Poles are roots, path is a locus. Of course, it's in a graph. Okay, so how do we plot that? Let's think about it a bit before we plot it. So over here I have G, let's just leave it at G, 1 plus Kg. As we have discussed, the K is not that important. K is greater than 0, but think that K is very small. If we consider K to be very small, in that case, this part is very small, very, very small. This part is infinity at the locations of the old poles. Exactly at the old pole, this is also infinity, this is also infinity. So that is no longer a pole if K is not 0. However, if K is extremely small, then very slightly far away, this is very big, this is now quite small, this is 1, and that is where the pole is. Okay, so for K going to 0, poles are open loop poles. Which poles are open loop poles? Closed loop poles are. For K going to infinity, this is an important question. So when K goes to infinity, it is not clear what is happening in this form, but let us write it as N over D plus K N. Okay, now remember that this has lower order than this. Okay, very good. However, when we look at it for any finite k, let me think about it with specific numbers. Okay, so let us say this is second order and this is fourth order. Then what is this? This is a fourth order polynomial. This has 4 roots. That much is clear. Okay, out of these 4 roots, 2 roots are going to be dominated by this second order polynomial. You see, I am looking for roots. Try to understand that. I am looking for places where this polynomial is 0. This k is very big. So if this k is very big and the whole thing is still 0, that means this n has to be very small. That means that for k going to infinity, 2 roots of the denominator polynomial are going to be very, very close to roots of n. That means open loop zeros. Okay, some go to open loop zeros. Okay, the others, what happens is there are only 2 values of s for which n is 0. For all other values of s, n is not 0. You are multiplying by k. That means it is some gigantic number. That can only be cancelled by some other gigantic number from here which does not have the benefit of k. That means the others go to infinity. Okay, alright. Let's go to MATLAB, which has a very nice program, built-in program called root locus. Okay, so here is G. It is a stable thing. It has 2 poles in the left half plane. Our prediction is that if we make a root locus plot of this, one of those loci will go to s equal to 2 and the other will go to infinity. Let us do root locus of G. There it is. You see, so here look, gain is 0.11, still a very small gain, that is the k, and the root is very close. Okay, gain here 2, I guess, about 2, and it is coming down. Over here at this gain 2.2, they are merging. Okay, but then after that the gain keeps increasing. Here is another gain, here is another gain. We had calculated that at a gain of 3 it will cross, right? Here is the gain of 3. You see it has crossed over, and then for larger gain it is just going to that one, and then larger gain the other one is going off to infinity. In this case it is going to minus infinity. This will always occur. So let me show you a really random example of fourth order. Okay, numerator d is equal to 7th order. Then I expect 3 branches to go to infinity, 4 branches to go to roots. I don't even know where they are, but just for an example, here is my transfer function. Oh, the other, sorry, d equals, this is my transfer function. Okay, so 3 third order polynomial, right? So 3 zeros of the numerator, 3 zeros of the denominator, 6 zeros of the denominator, that means 6 poles. Let me look at root locus of G. Okay, and you see that's what happens. 3 of them, these are large gains. You see this gain is 43,000. Over here also it will be 43,000 about, and then this is also some large gain. Okay, but then you come here, this has already started to diverge. This is 4,000. This gain here about 7,700 or so. Now let us zoom in over here and see what is happening. When you zoom in over here, let me make this picture big, you will see that this was one pole, this was one pole, this is 1 0, this is 1 0. The branch, root locus branch from this pole has just gone over to that one. You see gain is 0.9, gain is 3.9, gain is 12.9. It has basically gone over here, right? There were two poles here, they have gone off to infinity like that. There were two poles here and there was 1 0 here, right? 3 zeros, right? 1 2 3, 6 poles, right? 1 2 3 4 5 6, 1 2 3 4 5 6. From here one branch to infinity, from here one branch to infinity. Over here these two, they are coming and merging and splitting at this point. Over here gain is 3780, and then after that this one goes that way, even larger gain, and that one goes off to infinity. Okay, there is something else that I should point out, which is this is not on an equal scale. If you plot it on equal scale, then you will see the angles correctly, and when you do, you will see that this is basically 60 degrees, minus 60 degrees and 0. Okay, I can change it. I can pretend n is the negative of what it was, so I can say rather g is equal to minus g. It is the same thing, or you can think of it as negative gain if you wish, and then you can look at the root locus plot, and now the angles are exactly reversed. This angle is now 60 degrees, this angle is 60 degrees, and here is one branch that has gone off to infinity like this. Okay, so this is clearly a system. This system can be stabilized, but it is a system that will not be stabilized just by direct feedback. These are very troublesome. These fellows will, well, they will just come here. This is a hard system to stabilize. These poles, the root locus, no matter what you do, the root locus will typically come here. It will come to this one. Technically, mathematically, it can be stabilized, but in principle, in practice, it may be quite difficult. Okay, let's do another one. Let's say n is equal to rand this, d is equal to rand n 1 8. Now there will be 4 branches, right? G equals tf n d. And then we can look at the root locus, and when we do, you will see now there are 4 branches, right? 45, 45, 45, 45. So now you can see that if you have let me come here and it will be easier. So if you have RHP zeros, then for k large enough, closed loop transfer function is unstable. Okay, if numerator order is m, denominator order is p, k equals p minus m. Okay, if k equal to 1, we have one branch that goes to infinity, 1. Since it's only one branch, it can only be real. So this means unstable, this means stable. Very good. If k equal to 2, in that case, one possibility is one like this and one like this, guaranteed unstable. Okay, but another possibility is one like this and one like this, in which case if the imaginary axis is here, then this is stable, but if the imaginary axis is here, then it is unstable, right? Because it has moved over to the right hand side. So if k is equal to 2, this case, let me go back here. If k is equal to 1, this case means it's unstable, but stability is possible. It could be going the other way. If k is equal to 2, this case means it's unstable, but this case is also possible. In this, if the vertical asymptote is to the left of the imaginary axis, then stability is possible. If it is to the right, then stability is impossible, is not there. So for large k, so stability may still be possible for finite k. I'm sorry, you understand, it's only large k behavior, but stability is still possible. But if k is equal to 3, then either it is like this or it is like this. It doesn't matter. For large enough k, it will be unstable. If k is equal to 4, same story, right? If k is equal to 4, let me use this color here, k equal to 4, either it is like this or it is like this, right? Finally, you have to have 90 degrees between the spokes of the wheel, you know, and in this way, when the denominator order is sufficiently higher than the numerator order, then in this kind of control architecture, for large enough k, it will be unstable. There's just nothing you can do. Okay, so that's enough for the introduction to the root locus plot. We still have to think about how to draw the root locus plot. For that, I have a video which I will share with you.